Hello, hello. Yeah, I think we're started now. Bonjour tout le monde. Ah, great. A little bit of feedback. That is nice. I'm Etienne from Montreal, Canada. As you might have noticed, actually, first language French, but I will make this presentation in English. All right, so I'm not going to be able to see comments while I'm presenting, but I might alt tab in and out. And I have Remy right there who's going to act as my spotter. So if anything's wrong, and going to tell me about it. All right, so let's get started. Yes. Okay, so this talk is reactive programming patterns in Kotlin. My name is Etienne again. Hello, everybody. Nice to meet you. Small points to make before I get started. Big thanks to my employer, Shopify, who gives me time to prepare for these conferences. Also gave me time to travel, which today is not an issue, but still, I really appreciate their help in supporting all the speaker travel and presentations that I do. Also, a big shout out to the Google Developer Expert Program at Google. So it's Google's community program that helps people like me who have been very active in the community to basically be recognized, but maybe more importantly, again, support. So they give us all sorts of support, be it exposure or travel help or all these nice things. So a big shout out to Google, thank you. All right, so let's get started for real. What exactly is reactive programming? So here we have Wikipedia's definition. The key point here that we should remember is effectively that in computing, reactive programming is a declarative programming paradigm, which is concerned with data streams and the propagation of change. Those are the three main things right there. So, you know, that sounds kind of fancy. Oops, why did this happen? A sec, right back. No, just being picky. All right, so where were we? I see what's going on. Let me just take care of this. All right, small technical problems, but everything is good. All right, so all these nice little Wikipedia definitions sound kind of fancy. And the thing is that reactive programming is actually something you've been exposed to before, and that is downright mundane in some aspects. Case in point, the humble spreadsheet. Totally, absolutely reactive. Well, you don't believe me? Well, thing is, relationship between the data elements of each cell are encoded in a declarative way. You write functions in there, such as the function sum in the cell B5 right there. All these data elements are automatically reevaluated when anything they depend on is altered. So this is very much a reactive spreadsheet. And by extension, you can almost call it a reactive program. Well, at this point, you might be thinking, whatever, reactive paradigms and actions, spreadsheets are kind of, you know, simple and boring a little bit. To which I'd say, yeah, sure, all right. So how about this instead, Verilog? Now, Verilog, if you're like a proper nerd, that should get you a little bit excited, right? It's the hardware definition language of choice. So if you don't know what this thing is, not surprising, by the way, it's a programming language where you effectively declare how your hardware circuitry is going to be wired up. So it's used in electronic circuit designs a lot. So imagine that if instead of programming a CPU, you were writing a program that described how the CPU actually works, how it's wired up. That's sort of the idea here. So the little sample of code that you see right there is part of a program that allows you to drive a signal to an old school CRT. Remember those big vacuum tubes, electrons shooting in the vacuum? So anyway, this little sample is from a book called Designing Video Games in Verilog. Video game hardware in Verilog, right? So this is actually surprisingly approachable. I read this, I'd almost call it light reading, which is kind of weird, but it's, I think, not far from the truth. You can grab this thing for $10 and download it on your Amazon Kindle. It's kind of a fun read. And the little program right there defines basically all these things that you see below in the diagram, right? There's a lot going on for, like 9 lines of code? Anyway, I'm not suggesting we're going to study this in detail today, those are the two most extreme examples of reactive programming that are out there. So instead, let's get a bit more concrete, closer to what we know. So being said that reactive programming is declarative as opposed to imperative, that's the first point we're going to examine. So what is imperative programming? Well, it's effectively when you describe how to do something. So when your program is basically doing something like this right here, we have a for loop, right? And then what we do here is that we create a sequence of 1 through 5. We for through each of these items, so we get the numbers in succession. For each of those numbers, we check, is it divisible by 2? So if it has no remainder, when we modulo with 2, then we know it's divisible by 2. We add it to our mutable list. And at the end of all of this, we can display the result with our print line imperative result right there that we can see on the right at the output. The declarative version of this, right? So if imperative is how to do an omelet, right? Take out the pan, start the oven, put the butter in the pan, take out the eggs, etc. Declarative is going to the restaurant and just ordering 2 eggs over easy. So here we're just declaring that we want to filter numbers that are divisible by 2 from our sequence. A lot less code going on right there. And we're basically just saying what we want to happen. And then we're done. That's it. Same results. Cool. So the next thing that reactive concerns itself with is this idea of data streams. First off, in Kotlin, we can use coroutines to get the result of an asynchronous computation, right? And those are pretty nice. So here what we're going to be doing is adding a suspend function called calculated values. So this thing will return an int range again, same kind of example. So to simulate some work, we're going to add a delay in there. So you can see the coroutine icon in the slide right there. So that delay for a second and a half. And we finish all of this by returning the actual range. So we're going to pretend that this is asynchronous work. Cool. So we call the suspend function then from our run block. Our run block provides us with a coroutine scope in which we can call suspending functions. So when we start executing this, right, calculated values, execution will then run right into calculated values, the function, right up to the delay, where we're going to suspend for a second and a half. Then when the execution resumes, and our main function will get called back and complete, and we'll print out the computation result. So that's how you do asynchronous work using coroutines, the most modern idiom on Kotlin right now. So if we're thinking about a reactive approach, we need to be able to deal with streams of synchronous data, not only one result. So towards that end, we can use Kotlin's flows. First off, we're going to declare a delayed range flow. So the Kotlin asFlow extension function here that you can see is what turns a range into a flow. We get this with the Kotlin libraries pretty much for free. So then we add some behavior to our flow, and then we're going to do this using the onEach function. So onEach is more of a side effect function. So sometimes it can be a bit of a code smell if you start using this, but for our example, this illustrates things really well. So each time we want to emit a number from our range, we're going to be printing this little timer emoji and then wait half a second. So when we want to start off the sequence, what we do is that we call collect on our flow from the main function, and then we're going to start printing the values we get. So when we start the sequence, before each collection, we print the little timer, as explained, delay for 500 milliseconds, and then follow up and print the current item of the range from the flow. So we're only printing the one item right here, right? And then this code will execute again and again for each of the items in that flow. I was almost going to say stream. It's pretty much the same idea. We just created effectively an asynchronous stream of data, of values. All right, so we'll be calling everything in order, and that will exhaust the range, and then we'll terminate. Now, the other big concept we've hinted at so far is that propagation of change. So that idea is very useful in a lot of situations, but we're going to look at an example that will speak to us as a mobile developer. So let's think of the mobile app itself as a reactive system. If you think of it that way, an app will render to the device screen. Then the user is going to look at that screen, think a moment about what they're seeing up there. And in reaction to this, user's going to start pressing buttons, entering text, dismissing dialogues, etc., and so forth. So all these events come back to the app. The app processes these touch events. It's going to update some internal state, update the display, and so on and so on. So effectively, when you think about it this way, the user's input are what drive everything in this model. Whenever you hear the words propagation of change, think back to the simple idea, right? Like abstract away all the programming knowledge you have, just think about the user using their device and how this is effectively a reactive loop. So regardless of your app architecture of choice, reactive programming has been around for a while on Android. So for example, a lot of folks are quite familiar with RxJava. It's been around for years now. And there's a lot to love when you use RxJava to do reactive type work. So now that, given that today we're going to be exploring reactive patterns in Kotlin, look more at this as a list of must-have, right? These are things that we want to see in our apps that RxJava used to provide us. So I kept the really big bullet points here. We have Rx bindings, which was a way to basically turn your view events into streams of events. And then we had something called model store, which is more of a personal favorite. I'm not sure that everybody's aware of this pattern, but if you've done any kind of React or that type of work, the library Redux is very similar to what a model store provides you with. It's equally small. So we're going to see how to build these patterns and a few more using pure Kotlin code instead of using the RxJava library today. All right, so Rx bindings. We can use something called the callback flow function to roll our own here. So we're going to build an example and see how we could do this. So right now, we're going to try to build an extension function called clicks on top of views. So views, regardless what types of views they are, can handle clicks, and they can basically emit these things, right? So we're basically taking the simplest example, but you can translate this idea to whatever type of events you would watch and you would want to consume that are coming in from a view. All right, so in this specific case, this extension returns a flow of units. The idea is that every time a user clicks on a view, a unit will be emitted over the stream. So it might seem odd at first to have a stream of empty units, right? You're like, wait, this is kind of odd. If you're coming in from Java, it's like having a stream of voids. What's up with that? But if you think about it, it kind of makes sense. Android click events themselves don't actually carry any extra data. So you only need to know that they happened. And effectively what this is if triggering an event without having any data associated with it. So the other thing about Android is how all the handling of events from the view are traditionally callback based. That's what the SDK gives you. So luckily, we're going to be able to use a Kotlin library to handle all the nitty-gritty here, right here. And this library effectively is the callback flow builder function. So what's nice about callback flow is it gives us something called a producer scope. So producer scopes, we'll see in an instant, implement a few things, but they effectively provide you first and foremost with a coroutine scope. And if you're not entirely familiar with coroutines, but you're going to be familiar with this concept of scoping, the idea is effectively that when you are within the coroutine scope, you can call suspend functions. And you're in an environment where these things will work pretty much automatically, right? So once we have this producer scope, what are we going to do with it, right? Well, from within this block, the first thing we're going to be doing is creating a traditional view on-click listener. And then we're going to be assigning it to our parent on the second line, set on-click listener right there. So having access to producer scope, thanks to the callback function, we can do things that are related to coroutines. But as an extension function, what's kind of interesting here is that we also have access to the view, which is why we can call set on-click listener. Right? This might be a little bit confusing at first, but what you have to understand is we both have access to our producer scope and to the parent view. This is how this code makes sense. Now, The other thing to note about this tidbit, this snippet, is that we're calling offer right here. So the idea is that every time the user clicks the view, you call offer with unit. The offer function is something that is provided by the producer scope. So under the hood, this is because producer scope not only implements a coroutine scope, which gives us nice threading capabilities, but it also implements something called a send channel. So what we do is that when we call offer, the offer function is part of the send channel signature. So we're basically taking our unit and offering it onto that send channel. So that's what turns our click callbacks into a stream of click events. If we were creating a different type of extension function here, say an edit text one or edited text one, sorry, then in this case, we probably would not be offering up units, but we'd probably be offering some kind of string or character set, right? Just to say, this is the latest information I have from this event. This method can be used to basically create your own Rx binding calls for each of the view components that you want to be listening on and getting a stream of events from. Cool. Oh yeah, so last step when you use the callback flow function. So you must call await close. Now the idea here is that if you didn't add this, when you actually call clicks, the flow would immediately terminate. So that would basically do not much. When you call await close, what you're telling the coroutine scope is basically to suspend and only to continue and effectively remove the click listener once the flow consumer is canceled itself. So by creating this, when the subscription happens, we're going to be doing the binding with the event listener. We're going to start streaming these events. And when the flow itself is canceled because the environment it's part of gets closed down or shut down, then at that point, we're going to clear the listener automatically and execution will terminate for this little block. What's worth mentioning here is that this is an approach I effectively copied from Zach Swear's catch-up GitHub project originally. There's a few things that I've cleared out for the sake of the example here, but you can find a reference and a bunch of other references to a lot of material I used to prepare this talk in my GitHub repo. I'll be linking to all of this as part of the last few slides of the talk. All right, so we're going to move on to one of the key reactive patterns, the model store pattern. And this one is a pretty big one, and it's effectively the thing I think is the most useful in my day-to-day work with reactive programming. So at its core, the model store pattern is a specialized version of the reducer pattern that you can find in a lot of collection libraries. That's the example right here. So this is the Kotlin example of a reduce call on a range. So on execution here, this will just sum up the numbers that are in the provided range, right? It's going to add 1 to 2 to 3 to 5, so on, and this gives us a result of 15. Does that actually make any sense? Well, anyway, I double check this. Moving on. So one of the key ideas of the model store is this use of a reducer, right? So reducers are effectively a single function that take an old state as an input and return a new state out of it. So the key thing with reducers is that they're intended to be functional in nature. So that means that a reducer should not have state of its own. It should be idempotent, which basically means that if you call it with like a given input value, it should always return the same kind of output and all of this nice stuff, right? So you don't want to see any kind of side effects or any direct side effects when you call a reducer. That would be bad TM, right? The end goal is that once you have a few of these little reducer functions, you want to be able to apply them onto a model. So the model store is where that will happen. It's the engine that takes all these little reducers, applies them onto a model, and makes the model evolve in time. So we're going to focus here on what is behind the input process function in a model store. There's nothing specifically reactive about a plain function call, right? The idea is that it's mostly designed to help connect with flows of reducer. If, for example, you have flows of clicks, and you want to trigger reducers that will do some work on your model, then what you want to see happen is to create these flows and subscribe to them. And so the process function here makes sense. You don't necessarily know who's calling you, and you don't necessarily want to know. And the thing that is calling you might be a subscription, might be an imperative call, although it shouldn't be. But the key idea is that it's operating in a different working space, right? It's not operating on the same layer as you. It probably has different life cycles. So that's why we have this clear cut point here, which is not specifically reactive. You build reactive chains out of this. So internally, anyway, what we want to do, since we're sort of just getting a plain function call, is to rebuild a stream of reducers off of this so that we can get all the nice benefits of a reactive programming approach. So the way to do this with Kotlin is to use channels. So we've seen channels a few seconds ago when we were creating our view clicks listener. Channels, if you go into the proper definition for them, they allow you to have two coroutines. They allow two coroutines to communicate. So the idea is that, oops, go back here. So, okay, animations. All right. So the idea is that a call to the reducer offer function here will put up a reducer for whoever's listening on the other end, and execution will just keep going. So we're going to see in a second who's listening on this channel internally. Now, before we actually start processing that new stream, I'm going to show you how we're at the other end, we're going to be broadcasting our model state to all the consumers. So what we use on the other output end is something called a conflated broadcast channel. Now, it's a pretty fancy name. It's quite the mouthful, but the first part is it's a channel. So much like the reducer channel above, the reducer's channel, you can send value into that conflated broadcast channel and receive values from the other end. So people can listen in on this store channel and get results out of it. It's a broadcast channel. So broadcast here means that unlike a vanilla channel, you support multiple receivers. As you could probably guess, if you have a modeler in your application, you're probably going to want to have multiple subscribers that are getting data out of it. So that's how you get the broadcast part is what gives you this opportunity, this possibility of having multiple subscribers that will all basically get a multicasted notification whenever the model changes. The bonus point with this is that we get the AsFlow extension for free. So consumers will see a flow of states with all the API benefits it gives us. They won't be aware that under the hood, it's a channel. And lastly, conflated means that whoever subscribes to this channel only gets the most recently set value. Now that's important, and you don't want buffering to happen and to take place. So effectively, if a few events happen while somebody's not subscribed, you don't want it to replay everything that just happened, right? The example typically on Android is you rotate your screen, you unsubscribe for your model, which itself has a longer life cycle than your activity. And when you subscribe back, you're not really interested in finding out what happened while you were gone. You just want the current state. And that's what conflated means here. Like everything else has been dropped to the floor. All right. So now what we need to do is to figure out what the glue is going to be between these two channels so we can implement our model store. The goal is to take a series of reducers that we're getting from the reducers channel, changing this internal state of our model store by applying them one after the other, these reducers, and then making sure that the results of applying those reducers to the model are sent down into the store channel. So here's the line of code that binds everything together. It's one line of code, but it's a really dense one. So we're going to be breaking it down one step at a time and really looking at what it's actually doing, right? So first off, the store's starting state is going to be set at construction time. So here we're just going to have a store that has a counter inside of it, and we're going to set that counter to 0. Then when we receive our first reducer call, which in this case is basically going to be a click, and as you might guess, we're going to increment the counter every time we get a click. Then when we get this first event, we get it through the view that actually ends up calling our reducers channel. And that will be received here in the, badly named slice. You shouldn't be reading intents here. You should be reading reducers. Anyway, I won't correct it live. Can I correct it live? How fast can I fix this? You know what? It's not live coding, but I'm going to attempt to fix this very quickly. I think I'm going to give up in a sec. Am I giving up? Do I have it? All right, sorry for the contretemps. It's just too complicated to edit live. All right, apologies. So you have to read, instead of intents here, it's a reducer. So the idea is that on a channel, you call the receive function. When we call the receive function, this is a suspending function that will sit there and wait for something to come up on the channel. So at that stage, what's been happening here is that our piece of code is waiting on something to be received from the reducers channel. And once that is received, we call reduce on that reducer, passing in the old store value. So reducers, again, are something that take an old state and give you a new one. Now that we've done this, the new state is now effectively our old state plus 1. So we have changed the state. The next step is that we need to make sure to pass that onto the store channel so that any subscribers can get the latest updated state and our reactive chain goes on. Once we've done this, we can imagine that more reducers are coming in, are being applied to the model store one after the other, and so on and so forth. All right, so that was sort of to try to explain the breakdown of all the small details, but this right here is the complete code that you will ever need to create any type of model store. As you might even notice, it's a generic one. So effectively, this can store any kind of state in a reactive fashion, receive messages as input, reducers as input, and have multiple subscribers that listen into the change, that are listening to the changes that are made onto the model. So in the init block at the top, you can see the code that actually actively receives values, reduces them, and then broadcasts them by offering them on the store channel. And the rest of the code is fairly simple. Now, a couple things that need to be pointed out that were not necessarily clear from the slides before. You might be wondering why I use 2 channels at all here. So the goal for that is to allow the process function to be called from any other coroutine scope or context, while keeping the reducer calls themselves queued up only from the main scope. That ensures that we don't have any kind of threading problem or weird deadlock situations or any weird kind of mutations that would happen outside of a controlled environment. I say mutations, and that's actually a very poorly chosen word, because as you might have noticed, everything so far is immutable, and that's one of the key features of this pattern. Anyway, in turn, the fact that we are running these reducers from the main thread means that they need to be very lightweight. So if you're going to be doing heavy work and network calls, that work will need to happen in separate coroutines, and once it's done, you'll build new reducers from those results. I'm not going to be going into details of this today, but you'll find a lot of examples in the GitHub repos I'll be linking at the end of the talk. The other thing that's worth noting here, and I haven't mentioned, is that the close function right there. This can be used if you ever need to actually shut down a model store. On Android, very often you're going to have your models sort of live as singletons in your dependency injection system. So you might never actually need to call this if your model store has the same lifecycle as your application. But if for some reason you need a shorter lived model store, be it on Android or perhaps in backend code somewhere in Kotlin, this would be what you call to make sure everything shuts down properly. By shutting down the reducers, the store, and the scopes, we make sure that no work is going to be left hanging before we close down everything. Cool. So this is kind of nice. We just created a model store. It allows us to save our model state in a very nice and reactive way. So it might be worth to stop for a second and consider what exactly we want to store in there anyway. So quick review of the basics. What exactly is state anyhow? In computer science, as Wikipedia tells us, a system is described as stateful if it's designed to remember preceding events or user interactions. The remembered information itself is the state of the system. So that's pretty basic. So simplest example possible is that if you have a light bulb, it's either off or it's on. Nice. Right. So what about state machines then? Wikipedia makes them sound pretty complicated, but effectively the key bit again is one sentence. To paraphrase a bit, a state machine is a computation model that can be exactly in one of a finite number of states at any given time. So the light bulb in our model here is going to be either on or off, and not both at the same time, right? So if you think about it, then an event is something that happens that affects that system, right? And actions and transitions are when you switch from one state to another. And the event that causes that transition is the triggering event, or sometimes simply called the trigger. So those ideas are kind of interesting, especially if you think about our reactive system, right? We're passing events around, we're acting on those and triggering transitions, etc. So we can already see that there's probably some nice ideas that we can take from this and use in our own programs. So we're going to go from theory here to actual practice. I'm using code from the repository I'm linking below to show you a couple of ways that you can implement your own state machines in your own projects. This specific sample, though, is an adaptation of the Android architecture pattern to-do example app, and it's one that tries to implement this pattern using MVI. But the state machine pattern itself can be used with any kind of architecture. At its core, the way I'm using it in the sample is really to use it in a reactive way. In this sample, for example, it's mostly RxJava code, but you don't really care about all of that. The state machine pattern itself is usable from either an RxJava implementation or a coroutine and flow implementation of the model store. It really gels well with model stores. And we're going to try to see why that is. So we're going to take as an example a very simple state machine. The idea is that we're going to model what a pull to refresh process looks like. So pull to refresh, when you pull, the app loads information, it refreshes, shows us a bunch of new to-dos, right? Fairly straightforward. So if we have to model this in a state machine diagram, break out your UML and it looks something like this. So what we're really trying to do though here, if you think about it, is just to model a simple piece of asynchronous work. So typically we're going to be in idle mode, nothing's happening much. Somebody actually pulls on the screen, and then we start a refresh process. So when that happens, let's just look at what this state machine looks like in code. So when the pull to refresh happens, what we're going to be doing is we're going to start a new web query, an HTML query to get some info back from the server. And then we're going to eventually move on from the process state to a result state when that query comes back. So if the query succeeds, we're going to go back to idle after applying whatever, like finding that information that we just got and just like setting up somewhere. Or if that fails, that query fails, we're going to go into an error state where we'll, in this case, just copy the throwable that we just got to try to let the users consuming our model just display some error message to the user or handle that gracefully. Right, so in this sample, this is really, what we can do is really set up that state machine with a very simple sealed class, no frills whatsoever. The only fancy thing here is that we're storing that throwable if there's an error for reporting. That's all, right? So all this work is going to be backed then by an async aware reducer. So the state machine itself, to operate the transitions, we're going to need some code somewhere, and that code is right here. So you can see the idea of the reducers that are coming back again, right? So this pattern works really well hand in hand with the model store. So if we imagine that the model store is storing the state machine we just described, and that state machine can transition from one state to the next, and a model store, by getting reducers that tell it how to transition from one step to the next, will be able to reflect what's happening to other consumers. We don't even care which ones, but if you think about it, in our case, we had the view that was subscribed to this and displaying the spinner while we were processing. That's effectively what it was doing, right? It's getting its information off of a model store that would be storing this state machine. So if we go through the reducer builders here a little bit, when we start a query, we'll be moving the state machine from an idle state straight to the process state. And when that request resolves successfully or not, what we do is we fire off a new new reducer to move from the process state to either idle if that worked, as I was mentioning it before, or error if it did not. So that works fairly well if you have a simple state machine that backs your pull to refresh, right? Transitions here are all coded in your reducers. You need to be aware of what one reducer is doing, transitioning to the next. Very simple if you effectively only have 3 states, which are idle, processing, and or error. But what if we're tracking something a bit more complex, right? This example here, we're not that much more complex, but we can start seeing how the transitions are becoming problematic. So this state machine represents an editor screen. In the to-do example, there's a sample of this in the code, in the repo. What this represents is editing a to-do task. So you'd be clicking on a to-do task. It would bring you to an editor where you'd have title, description, detail screen, where you edit everything. When you're done, you press save, right? So if you're maybe making it a bit more complicated, an example, if you open any kind of document, your state machine is going to look something like this. You're going to go from a closed state where nothing in your state machine is being held, nothing's happening. Then somebody's going to decide to either add a task or a document or edit a task or a document, as you can see on the graph there. Those transitions are going to start happening. You're going to be editing the document. You can try to save it, delete the original document, etc. So this can become kind of messy. If you think about it, the sample code I showed you doesn't really give you any kind of safety or a nice approach that will sort of restrict a little bit what can happen. You could easily get into an illegal state type of situation where you transitioned erroneously from one state to the next. So I have like a little pattern I want to show last that helps with this. It's as follows. So again, I'm using sealed class to model a state machine. But you'll note that there's a big difference with the previous example. And the big difference is that for each of those states that you see on the graph, you can also see that the transition themselves are defined in the sealed class. And if you squint a little bit, you'll also notice that each of these functions are effectively reducers. So what do I mean by that? Well, they're hooked onto a state themselves, right? So if I take, for example, the closed state at the very beginning here, when my document is closed, somebody's going to try to either add a new document that we're going to edit or try to edit an existing one. So when I do this, I take the current state of my model store that's storing task editor states. I will be able to add or edit a task, and that's the actual transition, and that will return to me the next state in the chain. So I'm effectively doing here is I'm creating a bit of a DSL that says these are the legal transitions from one state to the next. And so by doing this, I'm basically helping the definition of future reducers, and I'm making sure that you can't really get into a situation where you're calling functions that are trying to delete a document when perhaps you're actually trying to actively save it right now. So all of these illegal state transitions just go away because there's effectively no way to even model them in your program. All right, so I'm coming up to the last slide where there's a few takeaways. I'll open up the floor to questions after that. And I even have the setup here so I can jump into code samples if anybody has like very specific functions or anything they'd like to see in action or something like that. So a couple of takeaways. Imperative versus declarative. So the big idea there is that declarative programming style allows you to avoid states in a very tidy way. State manipulations go away when you do declarative, And as you can see, I've also shown you a pattern that with the model store where you are able to still deal with state changes, but in a non-mutable way. You've seen how to create streams with the flow function, the flow class in Kotlin, basically the equivalent to RxJava's observables. The other thing we've looked at is model state managed immutably, right? So that's a very nice pattern that's quite key if you want to do a reactive approach to programming. Other note we just looked at, seal your state machines with a sealed class. And last thing I wanted to link to right here is my upvote repository. So there's very specific, like the examples for the flow model store are in that one. There's also a few examples of manipulating state. And a lot of the sample code I use on the slides comes from this presentation and little test sections. I tend to keep it up to date. So if you're curious, you should definitely look at that. And with that, I'm going to say a grand merci. And I'm going to toggle from presentation mode and start looking at the questions that the audience might have on this. If we have time, maybe Remy can tell me. Thanks, everybody. All right, so, all right, we have a couple of questions. So reducer cancel, running pending reducers, which might be outdated. Right, that's a good question. So what I do there is actually bake that into the state. What do I mean by that? So if you look back to, I'll quickly try to bring up my keynote. Thank you, folks. I'm seeing the thanks yous popping in. That's cool. All right, let me just double check how I can throw up the screen right there. I'm just going to show the diagram right there. So, right. So how do you cancel? What you need to do is to actually bake that into your model. So right there's a small example. It's kind of subtle and it's easy to miss, but right there you see the editing state right there. It has its own cancel transition. So that's not effectively exactly what the question is about. But if you imagine that you build this very, very simple one right here, right? I have effectively a process that's non-cancelable, but I can easily add the concept of the process being cancelable itself, adding that transition function on the state itself. And so what happens is that if you, for example, right, if we are editing and we went into saving, so somebody would press the save button, you'd go into saving. What I've done in the past when I want to allow the users to cancel any outgoing queries, I literally add a cancelable function right here. Either I will expose that as a button, a cancel button to the user, or I might even simpler just deal with it in a timeout fashion. So the idea is that your state machine also models your transitional states. So if you're saving something, if you're doing asynchronous work, you bake it into your state machine, and then you can also bake the transition functions to cancel everything into that. I hope that sort of answers the question. I think I'm rambling a little bit, so apologies. If that wasn't clear, ask a follow-up question, please. I'm happy to answer that. So is it possible to combine state machines with MVVM? Yes, absolutely. So the thing with the MVVM that Android sort of puts forward these days, and I say Android, I mean really Google and the platform, a lot of the backing stuff, well, so if you think about view models hooking up into repositories or models, a lot of the code examples we see nowadays are backed off of live data, which are effectively a reactive type approach. Personally, I would say that I would tend to stay away from live data. They have, I don't want to say they have problems, but they're fairly lightweight tools for what they are. Most of the big serious apps I've seen around that stick to the MVVM model tend to keep live data as their reactive stack for the view model layer. And then when they hit the model layer and there's more complicated work to be done, they're going to bridge that into RxJava. So I guess if there's one takeaway from the talk today is I would tell you, consider just using RxJava all the way or flows all the way, just like I showed you today. There's no real reason not to do it. Maybe the only thing to watch out for is to keep this idea that the view model is not a model. I've seen code very often where the line between the view model and the model are kind of blurred. So it's important to keep in mind that your view model on Android has a fairly short life cycle. It mimics effectively your view's life cycle, right? And this is, I'm putting the air quotes right here because activities and fragments have shorter life cycles than the views that they themselves sort of back, right? So what I'm trying to get at here is that I tend to reserve my state machine work for the model layer. And at the view model layer, what I'm going to be doing is preparing work for those other layers in a very functional way. Like I try to have almost no state, make sure that the model or repository is the source of truth, and that the view model layer is where you prepare the work for that source of truth. Any idea when these APIs will not be experimental? That's a good question. They asked me this 6 months ago, I would have said, yeah, they'll surely be out of experimental by March, right? So the thing to say though is that Flow is technically not that experimental anymore, I would say. It's been around for a while. It works rather nicely. Conflated broadcast channel is a good one. My understanding of it is that it's production ready, and experimental here might be more of a tag that says, and we have other stuff coming that will probably replace conflated broadcast channels to start with. I don't know if I have a link anywhere really handy, but if you just want to get into that subject, I'll actually copy paste a few links in the channel. Just Google for data flow in the JetBrains repositories. So there's a request up, I think it's a PR that's up, to add this concept of the data flow. And the data flow, effectively, I want to say, will replace the model store. It's very much like a conflated broadcast channel, but it's a flow in itself. It hides the channel details under the hood, but it's still a PR in draft. So I have honestly no idea when it's going to be out. That one was pointed out to me personally in something like, I want to say September of last year. And again, I had this impression it would be fast-tracked to greatness. And I know quite a few people look at that PR and there's super interesting comments there. Also, a lot of the code I have today is based off of how people are implementing model store-like structures off of the material that's sort of coming off of this PR, which is not yet public. So right now, conflated broadcast channel, I would use it in prod. Experimental, yeah, for sure, because it's probably going to get replaced with something nicer soon. Should you not use it? I think it's fine to use in production apps, but somebody else might know more than me. That may be a big boo-boo, so your mileage may vary. All right, cool. So thank you very much for your time. I'm just sad I can't see you all in person as usual, but I'm very happy that I got to present this stuff. Nice feedback on the chat. Ton of thank yous. Feel free to ask more questions in the Slack. I'll be checking it during the day as I go, and I'll probably dump my research notes in there too, just so people can look up links and start digging into those PRs I just mentioned. Merci tout le monde. À la prochaine.